So I've broken this up into two parts. We're going to cover chapter 8 and chapter 9 first. Here are the topics that you want to make sure that you are solid in your understanding on for chapter 8 and 9. The confidence interval estimates for a mean as well as for a proportion. And then we are going to cover required sample sizes for a mean and a proportion as well. And then for chapter 9, we're going to go through the two approaches to hypothesis testing, including the critical value approach and the p-value approach. And then we're going to run through a hypothesis test for a mean where the population standard deviation is known and not known, as well as for a proportion. All right, before we get into question 1, there's one key concept that I want to make sure that you pay very close attention to, and that's specific to the confidence interval estimate, the general format. So the general format for a confidence interval is going to be our point estimate plus or minus our critical value times our standard error. So we know that a confidence interval estimate is an interval developed from a statistical sample such that all of our possible intervals of a given width that are constructed, some percentage of these intervals, which is known as the confidence level, will include our true population parameter. So we build our confidence intervals around our point estimate from our sample, and then we calculate an upper confidence limit and a lower confidence limit. And so that's going to be our margin of error that we see here. With that said, let's get into question number 1. So in question 1, KPBS is interested in estimating the mean number of minutes per day that children spend watching TV. The population standard deviation is known to be 21.5 minutes. So this is a key point here. So we know that we're working with a situation where the population standard deviation is known. KPBS selected a random sample of 200 children and found that the average time watched by children was 191.3 minutes. We want to construct a 95% confidence interval estimate. So what is the margin of error? So the way I set up the slides is I'm going to walk through the different steps to approach this problem, and I'm also going to include the different Excel formulas that you would need to use to, let's say, for example, calculate the margin of error. So step 1 is we need to find our Z critical value. So we could do that in 3 ways. We could use Appendix F from the textbook. You could use your common Z critical values, which is right here, or you could use Excel. So we know that this is going to be a 95% confidence interval. So that's going to be a Z of 1.96. Now, if we were going to calculate that in Excel, we would use our norm.s.inv function, and then that would also give us 1.96. So step 2 is to calculate the margin of error. So for this one, we could either use a calculator or Excel. Here's our formula for the margin of error, and specifically to the right of the plus or minus sign. So we have our Z critical value, and then we have our standard error. So the population standard deviation divided by the square root of n, or our sample size. So we could just plug in our numbers from the story, and we would get 1.96 for a Z critical value times 21.5 for the population standard deviation divided by the square root of 200. And that gives us a margin of error of 2.98. We could also use Excel to get our margin of error directly without plugging in the formula or using the equation. Function in Excel is confidence.norm, and then the inputs are alpha, the population standard deviation, and the sample size. So here's an example of that inputs, and that would also give us 2.98. Let's go ahead and do that in Excel now to get some hands-on practice. So we know our sample size is 200. Our population standard deviation is 21.5. The sample mean was given to us as 191.3. So that's going to be our X bar. Our confidence level is going to be 95% or 0.95. So we know that our alpha, or our significance level, is 1 minus the confidence level. So we just type in 1 minus that and we get 0.05. So here's where you could either use the norm.s.inv function. It's also referenced right here to the right. So finding your Z critical value is norm.s.inv. We'll do it a couple different ways. For this one, we'll just go ahead and plug in 1.96. here is our formula. So for this particular one, I'm just going to do the math. So we're going to do equals 1.96 times the population standard deviation, 21.5, divided by the square root of the sample size. And we get 2.98. And so if we needed to calculate our lower limit and our upper limit, we know that that is our point estimate or our sample mean. So our sample mean of 191.3 minus 2.98, and then our point estimate of 191.3 plus 2.98. And so that will give our confidence interval estimate for this sample mean of 188.32 to 194.28. Question number 2, IHOP took a sample of 25 customers and recorded how long each occupied a table. The sample mean is 1.2 hours, and the sample standard deviation is 0.3 hours. In this case, the population standard deviation is unknown. What is the 95% confidence interval estimate for the mean number of hours a customer occupies a table? So we know this is a situation where we do not know the population standard deviation. So we are going to be using the t distribution here. Step 1 is to calculate the degrees of freedom. So that's going to be n minus 1. The sample size is 25. So 25 minus 1 is 24. Next, we're going to calculate our t critical value. You could use Appendix F or Excel. I do recommend Excel. So our alpha is going to be 1 minus the confidence level. We are going to use the t.inv.2t function. We're going to pass in alpha or 0.05 and our degrees of freedom of 24, and we get 2.0639. Here is our formula. Recognize the general format. So we have our point estimate plus or minus our t critical value. And then our standard error, the difference here is we are going to use our sample standard deviation in the place of our population standard deviation since it's unknown, and it's divided by the square root of n. So if we plug in all of the numbers, the t critical value of 2.0639 times 0.3 divided by the square root of 25, and you get a margin of error of 0.124. For this next problem, what I'll do is we'll use the Excel function to calculate our margin of error. So we're going to use our confidence.t function and pass in alpha, the sample standard deviation, and the sample size. And that also gives us 0.124. So our sample size is 25. Our sample mean is 1.2. Our sample standard deviation was 0.3. Our confidence level was 0.95. We're going to calculate our alpha as 1 minus our confidence level. Our degrees of freedom is 25 minus 1. So let's find our t critical value. So t.inv.2t. And then we're going to pass in our alpha. Make note that in Excel, they do call it the probability. That is our alpha. And then it's going to be our degrees of freedom. And we get 2.064. For our margin of error, let's go ahead and use the confidence.t function this time. So confidence.t, alpha, 0.05, sample standard deviation of 0.3, and then our sample size. And that gives us a margin of error of 0.124. All right, let's move to question 3. So this is a confidence interval estimate for a proportion. So 100 people were asked if they had health insurance, and 13 of them said they did not. What is the 95% confidence interval estimate for the proportion of people who do not have health insurance? So calculating the z critical value when you're working with proportions is going to be the same as when the population standard deviation is known. So you could use the common z values for 95% confidence interval, and we get a z of 1.96. Step 2, when we're working with proportions, we need to calculate our sample proportion if it's not given to us in the story. So the formula for the sample proportion for p bar is going to be x, our attribute of interest, in this case is 13, divided by our sample size. So plug in 13 over 100, and that gives us a sample proportion of 0.13. Now, with proportions, we will have to do this calculation ourselves. There is no function in Excel to give us the margin of error. So here's our formula. The general format is our point estimate is our sample proportion plus or minus the z critical value times the standard error of the sample proportion, which is going to be this p bar times 1 minus p bar divided by the sample size. So here I just kind of plug in the numbers into the problem, and we will get a margin of error of 0.066. So to calculate the margin of error, you could either use a calculator and just plug in these numbers, or you can use Excel. Here is the Excel formula. So 1.96 times the square root of 0.13 times 1 minus 0.13 divided by 100, close parentheses, and that will give us 0.066. Our sample size is 100. Attribute of interest, or X, is going to be the 13 people. Our sample proportion is going to be the 13 divided by N. We'll go ahead and plug in 1.96 here for our Z critical value. And now we're going to calculate our margin of error, and we're going to do the calculation right here to the right of the plus or minus sign. So we're going to say equals the Z critical value times the square root of our sample proportion times 1 minus the sample proportion divided by 100, close parentheses, and we get 0.06592. Let's go to question number 4. So Honda wants to estimate the mean household income for college students who own a car. If the company wants a 90% confidence interval estimate with a margin of error of plus or minus $2,500, what sample size is needed if the population standard deviation is known to be 27,500? Similar to the confidence interval estimate, we need to calculate our Z critical value. This happens to be another one that's in our commonly used Z values for 90%. That is going to be a 1.645. This is going to be the same for the confidence interval when the population standard deviation is known. So we have our 1.645. And then step 2 is to calculate our required sample size. Here's our formula. We're going to take a Z critical value and square it, the population standard deviation and square it, and then our desired margin of error squared. So if we plug in these numbers from the story, we're going to get a sample size of 327.43. And remember, we always want to round up with our sample sizes to get the next whole number. So with the required sample size when a population standard deviation is known, the two options for you is to use your calculator or Excel. Here is our Excel formula. And so we get the 327.43, and you always want to round up. There is a SS mean, so sample size, SS, that's what it stands for. So this one is a 90% confidence level. Population standard deviation is 27,500. And so when we're calculating our sample sizes, in this case, we're given the margin of error, and then we are trying to calculate what sample size we would need to achieve that level of confidence with that margin of error. So it's very similar to a confidence interval estimate, but now we're trying to calculate what sample size we need. So the margin of error was given to us as 2,500. Z critical value is 1.645. So the required sample size is Z critical value squared, I left out the 2, times the population standard deviation squared. You want to put this all in parentheses to ensure our order of operations are done correctly. And then we're going to divide by our margin of error squared. So that's going to be the 2,500. So we get 327.43, but always round up your answer. Question number 5. The required sample size for a proportion. MiraCosta College wishes to estimate the proportion of students who take online classes with a margin of error of 0.01 with 95% confidence. So there is no pilot data. what is the required sample size? So when we're working with proportions, our Z critical value is just going to be the same as when the population standard deviation is known. 95% confidence we know is a 1.96 Z critical value. Step 2 is we need to calculate our sample proportion. However, we were told that there was no pilot data, so we don't have that information to calculate the sample proportion. So we are going to use 0.5 to be conservative. And then the next step is to calculate our required sample size. Here is our formula when we're working with proportions. So we're going to take the Z critical value squared times P times 1 minus P divided by the margin of error squared. Plug in our numbers, and we get a sample size of 9,604. Here's our formula in Excel that we're going to do right now. Sample size proportion. So we have our 95% confidence level. Our margin of error was given to us as 0.01. We don't have a sample, so there's no pilot data. So the estimate for the population proportion is 0.5. Z critical value is going to be 1.96. And now we're ready to just plug in our formula. So we'll do equals our Z critical value squared times P times 1 minus P divided by our margin of error squared. And then we get 9604. So that wraps up chapter 8. Let's go ahead and move to chapter 9. Let's do a little quick recap of the two approaches to hypothesis testing. So the first one is the critical value approach. This is where we're going to calculate either our lower or upper critical value. So in this case, our hypothesis is the population mean is less than or equal to 25. And then our alternative hypothesis is that the population mean is greater than 25. So as you know, when we look at our alternative hypothesis, we see our sign is pointing to the right. So we know that this is going to be an upper tail test. Here is our cutoff value. And this region is alpha. So this is the region where we will reject our null hypothesis. So if our test statistic is greater than our critical value, we reject. The alpha in this case is the probability of committing a type 1 error. So whether it's a Z or a T value based on the significance level, this is what determines if we're going to reject or not reject the null hypothesis. The other approach is the p-value approach. In this case, the p-value is just the probability, assuming that the null hypothesis is true. So we're assuming it's true if this is the probability of obtaining that test statistic that is at least as extreme as the test statistic that we calculated from the sample. So with the p-value approach, it's much more straightforward in our hypothesis decision. So if our p-value is less than our alpha, then we reject the null. If it's greater than or equal to our alpha, we do not reject. With our p-value approach, it's more than just a reject decision. The further the p-value is from alpha, so like if it's very close to 0, then we have a stronger decision for our hypothesis test. So you want to watch out in the problems if it's asking for you to do the critical value approach or the p-value approach. So question 6, McDonald's wants to test whether the average volume for their milkshakes is 16 ounces. The population standard deviation is known to be 0.20 ounces. Assume that the hypothesis test is to be performed using a 0.10 level of significance, or alpha. They took a random sample of 64 shakes. They measured the size of the milkshakes, and the sample mean was 16.04 ounces. So in this problem, the hypothesis statements were given to us. This is a two-tailed test. So our null hypothesis is that the population mean is equal to 16 ounces. And our alternative hypothesis is that it's not equal to 16 ounces. So just remember that the null hypothesis will always have the equality sign. Here's a little visual of our decision. So this is a two-tailed test. So we would reject the null hypothesis if our test statistic is in either tail, the lower or upper tail. First step is to calculate our Z critical value. So you could use the appendix or the common Z values or Excel. So the level of significance is 0.10. So that is a 90% confidence level. So we know that's 1.645, but here is our formula for reference using the norm.s.inv function because our population standard deviation is known. So the next step is just to calculate our Z test statistic. We could use a calculator or Excel. Here is our formula for the Z test statistic. So in the numerator, we're going to calculate our sampling error. So we're going to take the sample mean, subtract our population mean, and then divide by the standard error, or our population standard deviation divided by the square root of our sample size. So if we just plug in our numbers here, we will get a Z test statistic of 1.6. Here is the formula to do this in Excel. So what is our sample size is 64. Population standard deviation, 0.20. Our sample mean is 16.04. What is our hypothesized population mean? So we're hypothesizing that we have 16 ounces filled. So we will use the number that it's in our hypothesis statement. So that's going to be 16. And then here, the significance level is given to us. So we'll just plug in the 0.10. I'm going to go ahead and do the Excel function this time, just so you have the practice in case it is for a confidence level that it's not in the common Z values. So since this is a two-tailed test, we do need to use the absolute value function. So it's going to be abs.norm.s.inv, and then since it's a two-tailed test, and then divided by 2, close parentheses, and then close parentheses for the absolute value. And that gives us a 1.645. So we know that our commonly Z values are correct here. This is how you could do it if you had a different significance level. So here's our formula for the Z test statistic. So we're just going to take our sample mean, subtract it from our population mean, and then divide it by the population standard deviation divided by the square root of our sample size. Let's put our denominator in parentheses just to make sure. And then let's also put our numerator in parentheses to make sure we get all of our order of operations done correctly. And that gives us 1.60. You need to use the critical value approach. I do have the p-value box in here in the case that you do need to calculate the p-value. But in this case, we're going to use our critical value approach. So since 1.6 is less than 1.645, our distribution curve, so we know our critical value cutoff is 1.645, and 1.6 is lower. So it's going to be right in here in the white area, just right under it. So this is going to be our do not reject. So we're not going to reject the null, and we can conclude that the shakes are properly filled at 16 ounces. Samsung claims the Galaxy S9 will last more than 8 hours of talk time when the battery is fully charged. To test this claim, a sample of 18 phones were tested. The results showed a sample mean of 8.2 hours and a sample standard deviation of 0.4 hours. The population standard deviation is unknown. So we know we're going to be working with our T distribution. Calculate the hypothesis test using a 0.05 level of significance. So the first step here is just to visualize our hypothesis. So we know that Samsung is claiming that the phones last more than 8 hours. So we know that our alternative hypothesis is that the population mean is greater than 8 hours. And then our null hypothesis is going to be that the population mean is less than or equal to 8 hours. So our alternative hypothesis points to the right. So we know we are dealing with an upper tail test. We're also going to be using the p-value approach on this one, but we will calculate both the critical value and the p-value. So let's calculate our degrees of freedom. So we have a sample size of 18 minus 1. That gives us 17. Calculate the t critical value. So you could use Appendix F or Excel. We're going to be using the t.inv function. This is an upper tail test. So we're going to take 1 minus 0.05 and then our degrees of freedom of 17, and we get a t critical value of 1.7396. Next step is to calculate the t-test statistic. Here is a formula. This is similar to Z. We have our sampling error in the numerator. What changes here is instead of the population standard deviation, we are going to use our sample standard deviation, S, divided by the square root of n. So if we plug in our numbers here, we're going to get a t-test statistic of 2.12. You could use a calculator to calculate that or use Excel. And here is our formula if we were to do it in Excel, which we're going to do it here in a moment. And then next, we need to calculate our p-value. So for the p-values, you can only use Excel. So to calculate our p-value for our t-distribution, this is why it's important that you understand that it's an upper tail test, because in this case, the function is a different function. So since it's an upper tail test, we're going to use the t.dist.rt function. We're going to plug in our t of 2.12 and our degrees of freedom of 17, and we get a p-value of 0.0245. Let's plug in the sample size of the 18 phones. Sample standard deviation, 0.4. The sample mean is 8.2. The hypothesized mean is going to be the 8, and then our significance level is 0.05. Let's calculate our degrees of freedom as 18 minus 1. Our t critical value is going to be t.inv 1 minus 0.05 for our upper tail, and then our degrees of freedom, and we get 1.740. Here's our formula for our t-test statistic. So we're just going to do equals 8.2 minus 8, close parentheses, and then we're going to divide it by the sample standard deviation divided by the square root of the sample size of 18, close parentheses, and we get 2.12. And now we're ready to calculate our p-value. So we're going to t.dist. So you can see the pop-ups there. This is going to be your lower level. This is going to be your two-tail test, and this is going to be your upper right tail. So we'll just select that function, and then we're going to plug in our t-test statistic, and then we're going to plug in our degrees of freedom. So remember I mentioned about the little pop-ups here. So it says degrees of freedom. In the prior one, it was sample size. So just watch out for the inputs on these functions. We do 17, and we get a p-value of 0.0245, rounded to 2 is 0.02. Let's go back to our slides now. So our alpha is 0.05 and our p-value is 0.0245. So we know using our p-value approach, since the p-value is less than our alpha, we know that that is a reject decision, and Samsung's claim is that their phones do last more than 8 hours. When we come to our hypothesis decision, you also need to look at it from the business lens. So in this case, they're trying to claim that their phones last long, or in this case, 8 or more hours. So the data supports that claim. All right, question number 8. We're going to wrap up chapter 9 review, and we're going to do a hypothesis test for a proportion. So Carlsbad wants to build more lifeguard towers on the beach. City leaders believe that more than 60% of residents support the idea. A poll of 195 residents is taken, and 125 of them said they support building more towers. Using a 0.10 level of significance, conduct a hypothesis test using the following hypotheses. So our null hypothesis is that the population proportion that supports building more lifeguard towers is less than or equal to 0.6. So the equality sign is in the null, And then our alternative hypothesis is that it is greater than 0.6. So let's visualize the distribution. So we know that the sign is pointing to the right. So this is an upper tail test, and this is going to be where our rejection region is going to be. The sample proportion is going to be P bar is going to be X, or attribute of interest, divided by a sample size. So 125 divided by 195 gets us a sample proportion of 0.641. Step 2, when we're dealing with proportions, we will always be working with Z values. So you could use a calculator or Excel to calculate your Z test statistic. Here is our formula for proportions. So we're going to take our sampling error, our sample proportion minus our population proportion, divided by the standard error for the population proportion, which is going to be the square root of P times 1 minus P divided by the sample size. So again, working with proportions, you're always going to have to either use a calculator or Excel. There are no functions. So if we just plug in our numbers from the story, we'll get a Z-test statistic of 1.17. Here is the formula that we'll be implementing in Excel to calculate the Z-test statistic. We're going to use the p-value approach for this one. So working with proportions, we'll always be working with a normal distribution. But in this case, you want to watch out. It is the norm.s, so the sampling distribution. And since it's an upper tail test, we're going to do 1 minus that. So 1 minus norm.s.dist. Then we're going to plug in our z, and then true for cumulative. So we're calculating it up to the right. So we have a proportion tab. So our sample size was 195. 125 of them supported it. The hypothesized population proportion. So it says here that they claim that more than 60% of the residents support the idea. So we're going to plug in 0.6 for the population proportion. Our significance level is 0.10. Let's calculate our sample proportion as X over N. So our Z-test statistic is going to be our sample proportion minus our hypothesized population proportion divided by the square root of our population proportion times 1 minus population proportion divided by the sample size. So this is why I included the formulas on the slide so that you can cross-reference when you guys are practicing for the exam. So that gives us a Z-test statistic of 1.17, and we're going to calculate our p-value now. It's going to be 1 minus norm.s.dist, our Z-test statistic, and then true for cumulative. And we get 0.12. Let's go back to our slides here. So what is our decision using the p-value approach? So since the p-value of 0.1210 is greater than our alpha, so in this case, it's greater than alpha, we do not reject the null. And so we will conclude that the proportion of residents who support more lifeguard towers is not greater than 60%. So we're not rejecting this null hypothesis.